everyone, my name is Danielle Gonzalez. I am a PhD student at Rochester Institute of Technology, and I'm going to be talking about a project I did last summer at Microsoft Research in Redmond, Washington with Tom Zimmermann and Nagappan. Our project was called The State of the ML Universe, 10 Years of Artificial Intelligence and Machine Learning Software Development on GitHub. Artificial intelligence and machine learning are ubiquitous terms now in software engineering. In fact, the Evans Data Corporation in 2009 released a report that estimated 7 million developers use AI and ML in their development work, and they also expected that within the next 12 months, another 9.5 million developers would begin to use it. This also reflects GitHub's own findings, as shown in their State of the Octoverse reports. They had a comment that repositories with topics such as deep learning were becoming more popular, and over the years, there's been a growing community focused on data science. This project essentially is turning the state of the Octoverse into the state of the MLverse, sort of figuring out what the community looks like. And we did this by characterizing it similar to the Octoverse report, and we wanted to highlight what makes the community unique and not just report on these values. So we did a comparison with a set of non-AI and ML repositories as well. To actually apply it, we asked ourselves, what should be accounted for in future AI and ML repository research? So we looked at 3 types of repositories. First of all, we split AI and ML repositories into 2 types, tools and applications. So AI and ML tools are projects that develop new frameworks, libraries, algorithms, or actual tools that you can use for AI and ML. And an example of this is TensorFlow. It's actually the most popular AI and ML project. And applied projects use these tools towards solving a specific problem. And my example here is face swap. I'm not sure if you would consider that a problem, but they use deep learning to enable face swapping in video. And our comparison repositories are simply projects that don't develop or use any of these technologies. An example from our data set being Homebrew. So we have a fairly simple approach to collect the data, just 4 steps. The hardest problem to solve was how to find the repositories related to AI and ML, and we used the topic labels. We did a search for all of the topics that are related to machine learning, artificial intelligence, and deep learning. And we actually found 439 labels. And they were usually subsets, specific technologies, or approaches, like the one examples given. So then we needed to collect repositories with these labels and the relevant data. So we used the GitHub API and GHTorrent to search for repositories that had at least one of the topic labels, and then we collected all of the metadata we could from the API and GHTorrent for each of those repositories. And from our initial search, we got 53,427 public repositories related to AI and ML. We also used a similar approach for our comparison set, where we used the API and GHTorrent. But this time on the API, we searched for repositories that had commits within 2019 and then sorted them by stars. And then we collected all of the relevant data for the repositories we got back. So we collected 100,000 public comparison repositories. We went through a filtering process, adapted from best practices. And I say adapted because we wanted to be a little less restrictive than most works want to be, because we're looking at an entire community. So we don't want to restrict ourselves to only the most popular repositories. Our filtering criteria for size, popularity, activity are probably less restrictive than other work, but we believe that this approach gives us a representative sample of the entire community. So once all of this was complete, we had our final data set. The figure on the left shows the breakdown by repository type and account type. You'll see that users own more repositories in every category. In total, we had 9,323 repositories. 4,524 were applied AI and ML. 700 were tools. 4,101 were comparisons, so no AI or ML used in them. So moving forward with our characterization, we started with a timeline. We wanted to know when the first AI and ML projects were created and the ratio of AI and ML projects to our comparison projects over time, because we wanted to pinpoint when the AI and ML boom actually occurred on GitHub. So as you can see from the figure, the darkest color is the comparison set, the greenish color is tools, and the bluish color is applied. The first AI and ML repositories were created in 2009, the oldest being CI-lib, which is a computational intelligence library written in Scala. The boom really and by boom I mean when more AI and ML repositories were being created than comparison projects, was in 2017. But the proportion has been increasing since 2012. So essentially we have 10 years of AI and ML development. We also looked at what types of users interact with these repositories. We defined two different types. There are internal users, which are the contributors. They're authoring and pushing commits, they're maintaining the repository and artifacts, for example, opening and closing issues, pull requests, leaving comments, code review. And then we have external users who just open issues and leave comments. And so we looked at the distribution for each repository type of internal and external users. And we found that AI and ML tools had the most internal users. TensorFlow had the most out of anyone, 1,690 contributors. And the comparison dataset had the most external users, with Microsoft's Visual Studio Code having 46,559. Looking at popularity, in this case, we did not do a comparison set because we collected that data by sorting by stars, so that would be biased. So here we have all AI and ML together, and then applied and tools. So the median number of stars for all AI and ML repositories was 37, but tools are usually more popular than applied projects. If you're noticing a pattern here, we have TensorFlow again with over 130,000 stars. Python is the most commonly used language for AI and ML development. In our data set, 56.8% of the projects used Python, 58% of applied types use Python, and about 43.85% of tools use Python. In the comparison set, the most commonly used language was JavaScript. And you can see from the heat map figure some of the other languages that were used in the AI and ML dataset, including Jupyter Notebook, C++, Java, JavaScript, R, Go, C#, and C. So after we looked at sort of the front-facing characterizations of these repositories, we wanted to take a bit of a deep dive, and we developed a quantitative approach to measure collaboration and autonomy within a repository. So why would we do this? First of all, the measurements reflect the contribution models used on GitHub. If most of the contributors can directly push and commit their code, it's likely a shared repository, and the contributors have high autonomy. They're not dependent on someone else to merge their contributions for them. If most contributors have to submit the pull request, then it's likely the fork and pull model, and that would indicate high collaboration. Also, prior work found that these specific measurements influence developers' perceptions of productivity, and they can be measured at the team level. So this is a way to sort of look at productivity of an entire team without isolating specific developers. So normally these measurements are taken qualitatively, such as with interviews with developers. And this can be difficult, time-consuming, and cost money if you need to pay your study participants. So we wanted to see if we could measure this with just the repository metadata that we collected for our characterization. And to make inferences about the AI and ML and our comparison communities, we aggregated measurements from each repository. So this figure here is just the median number of each artifact type per repository type. The key thought here is that commits are not the only way that two users can collaborate within a repository. So we actually defined 5 user-to-user collaborative interactions that we could use to quantify collaboration. We have contribution interactions, maintenance interactions, process interactions, review interactions, and discussion interactions. So contributions are an interaction between the author and committer of a single commit. Maintenance is 2 users initiating an event for the same issue or PR, so neither of them is the reporter or opener. A process interaction is between the reporter or opener of an issue or PR and another user who initiates a maintenance event. So for example, the owner of the issue and the person who's adding a label to it. A review interaction is between the author, reporter, owner of an artifact and someone leaving a comment. And a discussion interaction is between two commentators from one of these artifacts where neither of them is the author. We parse artifact, event, and history data from GHTorrent for every single pull request, commit, and issue, for every single repository, and we created what we called an interaction record for each instance, which held the relevant data. And with this information, we developed measurements for two perspectives. The first is users per artifact, so how many unique users have collaborative interactions with each type of artifact, and how many interactions per type does each artifact usually have. For individual repositories and sets of repositories like our AI and ML community, these measurements can be used to identify patterns. So with our data set, issues had the most user interactions for each repository type, followed by pull requests and commits. And in our AI and ML repositories, the tools had more collaborating users than the applied projects. Looking at interactions per artifact here, these figures are the distribution of interactions per artifact for each repository type. So in all groups, discussions were the most common interaction for issues and pull requests, and contributions were the most common interaction for commits. The most common interaction for AI and ML repositories was commit contributions, and the tool repositories had more of most of the interactions than the applied projects. Looking at autonomy, we wanted to measure whether a team was autonomous. And to do that, we say if the majority of contributors can author, merge, and commit their own changes, then the team is autonomous. So to detect this, we built records of every user to artifact interaction. And then each user's records were then parsed to count how many times they had each role. We classified each contributor into a user type. We have maintainers, we have autonomous contributors who the majority of their commits are self-committed and the majority of their PRs are merged by them. A dependent contributor, the majority of their commits were not committed by them, and a majority of their pull requests were not merged by them. So to determine team autonomy, we computed the proportion of each user type. And to infer about the AI and ML community, we looked again at distributions of these measurements across the community. So for user type proportions, we have the distribution of user type proportions by repository type. And all of the AI and ML repositories had a median of 33% autonomous contributors, and applied projects had the most autonomous teams. The applied AI and ML project group in our data set had 1,777 autonomous teams. However, most of the AI and ML repositories were not autonomous. What can we do with this information? So we put together the considerations for future SE research. First, most of the software is written in Python. So this should definitely be a focus for any future research. Individuals and organizations own these projects, and these groups might have different motivations and expectations that should be accounted for when looking at their repository data. Internal and external users have different characteristics. So when you're looking at who's interacting with the repository, it's important to make this distinction. TensorFlow is the most popular AI and ML repository, and it should serve as the baseline for future research. Collaboration is multidimensional. Although commit contributions are the most common, discussion and review interactions were also very common and shouldn't be discounted in research. Applied AI and ML repositories had more autonomous teams than the tool dataset. These two repository types have distinct characteristics. And finally, collaboration metrics can be applied to specific artifacts. In this work, I've focused on the aggregation within the communities and the different repository types, but you can use these metrics to look at fine-grained details and patterns within a single repository as well. If you have any questions or comments, please join our Q&A session, or you can contact me.